Hello, welcome back. This is Calc 1 by Dr. Oz. Today we're going to go over the revision of Chapter 4, which is all about applications of differentiation. Hopefully at the end of the day, we're going to have a good digest of whatever we covered in Chapter 4. At this moment, let's quickly summarize the learning objectives of Chapter 4. We started off with understanding the definition of an extrema on an interval, and in fact we extended that definition on an open interval, and we finalized that by finding the extrema, relative extrema on a closed interval once the function description is provided to us. And next we had one of the nicest applications of differentiation is called Rolle's theorem, and that is a natural extension to Mean-Value Theorem. So we sort of had some problems, example problems to understand that concept. And we also worked on increasing and decreasing behavior of the function together with its concavity. And we had the first and the second derivative test to pinpoint relative extrema of a function. And we also worked on investigation of the inflection points for the graph of the function. And we had finite and infinite limits at infinity, so that in fact led us to two different asymptotes. One was the horizontal, the other one was the slant asymptote. And also we had the whole analysis of sketching the graph of a function without using a calculator. And I skipped this section about applied maximum and minimum problems, but we still kept the concept of tangent line approximation and differentials idea. And we also had a few applications on the estimation of a propagated error using a differential, and find a differential of a function by using the differentiation formulas. And here's the WebSI we use, so side by side you can actually go through, certain concepts together and then check out the homework problems associated with those. Well, we started off with the minimum and maximum definition of a function on an interval, and we said that f of c is the minimum of f on an interval if f of c is smaller than or equal to any other function value on the same interval. So, and then we said the same or similar definition for maximum, and we say that f of c is a maximum as long as f of c is greater than or equal to any other function value on that interval. Okay, so we had that part as well, and we called those values to be extreme values or extrema, and there are alternate definitions of those, and then we can use absolute maximum or absolute minimum, global minimum or global maximum, and we also concluded that the endpoints could be like good candidates for relative extrema, so we have to be careful about the endpoint extrema. And then we finished this section, we finished this argument by stating this fact that that's called like extreme value theorem, which essentially states that if you have a continuous function on a closed interval, then for sure you're going to have a minimum and a maximum achieved on the interval. Okay, so this is a very important fact, and you're going to use it time to time. Okay, and we sort of dove in further in defining the relative extrema, and you can check those by yourself in your own convenient time. But here I want to more focus on the definition of critical point, because critical points or critical numbers are going to be used all the way in this chapter. So what is a critical point? A critical point is a point where f prime is 0 or undefined. Okay, so essentially to pinpoint critical numbers, you're going to look at the first derivative, and then you're going to solve the first derivative set equal to 0. And if you have a solution, those solutions are called critical points of the first type. And by looking at the same f prime, if there is any point that makes it undefined, so that's going to be the critical point of the second type. Okay, so by defining the critical point, we had this fact listed here. that if f has a relative maximum or minimum at x equals c, that point has to be a critical point. So you see how important to come up with the critical points, because if your function has relative extrema, those points have to be critical numbers. Okay, so we talked about that, and I think we finished this section by putting this guideline of finding extrema on a closed interval. Let's say like we're given a function on a closed interval AB, and here are the steps that you should take. Find the critical numbers of f. By going back to here, you're going to deal with f prime essentially. So find f prime, and f prime hides the information about critical points. And you evaluate the function at the critical points, and as well as the endpoints. So number 2 and number 3. So you're going to evaluate f at the critical points and endpoints, and the least of those values would be the minimum, and the greatest is the maximum. Okay. All right, let's continue to 4.2. All right, let's continue with 4.2. We had the Rolle's and the Mean-Value Theorems covered in that section. And what is it essentially saying? Let's check that out. Let's say like we have a continuous function defined on the closed interval AB, and let's say you have a differentiable function on the open interval AB. If f of a equals f of b, then there exists at least one number c within the interval AB such that f prime is exactly equal to 0. So you have in fact 3 conditions to check whenever you want to apply the Rolle's theorem. First condition is that you will be checking f is continuous on the closed interval. Second, f is differentiable on the open interval. So these 2 conditions should be checked before you hit the road. And then the third condition, you should also double check that f of a, see like f of a and f of b are exactly the same on the graph here. Okay, so that there exists at least one point for which the f prime is exactly equal to 0, which essentially means that you will have a horizontal tangent line. And this could be happening more than once. This graph represents only one, but if you have, let's say, a function like this, right? Still f of a equals f of b, but as you see that you have 3 instances where f prime of c is equal to 0, for which you have a horizontal tangent line. Okay, there's a slightly different version of that. It's called the Mean-Value Theorem. The conditions are the same except the third one. So the first and the second conditions are exactly the same, but we don't require f of a to be equal to f of b. Instead, we in fact want them to be different, so that the slope of the secant line on the interval AB is achieved by a tangent line. So you will have exactly the same secant line achieved at an interior point as a tangent line to the graph. So as you see that in this representative example, the interval is 1 and 4, and here's the secant line connecting the endpoints of the interval. So this same sort of like line is achieved in a parallel way within an interior point. This is exactly the tangent line at that point. So, all right, the next section that we're going to go over is 4.3. In 4.3, we had increasing and decreasing functions. We were trying to, in fact, find open intervals on which the function is increasing or decreasing. So we had the definition of what means to be increasing or decreasing on an interval, and in fact increasing decreasing concept is tied up to the first derivative of the function. Like in critical points, remember we were working on f prime, and for increasing and decreasing behavior of the functions we will be also working on f prime. So all we're going to do this time is to check the sign of f prime on the given interval or subintervals. Okay, so if f prime is positive, we deduce that f is increasing on AB, and I use this notation I remember. And if f prime is negative, then f is decreasing. So f is decreasing. Here was the notation I used. And if f prime is equal to 0, f is constant. And this is, don't sort of like get confused with here with the critical points, because f prime of x equals 0 for all x, and we know those functions are constant functions. Okay, so if f prime is 0, that means it's just constant for all x. Okay, so we had this sort of like fact about increasing and decreasing functions. So all we're going to check again is to investigate the sign of f prime on the subintervals based on the critical points. Okay, and I in fact gave you a guidelines for finding intervals in which a function is decreasing or increasing. So first, obviously, we locate the critical points of f and use those numbers to test intervals. Okay, so we were having like sample numbers or test values from each subinterval, which are in fact built by the critical numbers. Okay, and then based on those like test values, we determine the sign of f prime, and based on that, we deduce that f is decreasing or increasing on the corresponding subintervals. Okay, and you can always change those intervals to infinite intervals depending on what the function you're dealing with and what the in fact interval provided in the question to you. And we also had a definition saying like a function is strictly monotonic, it's increasing or decreasing, on an interval when it's either increasing or decreasing on the entire interval. Okay, so if you see a function like this, let me just get a good color here. If you see a function like this, that's increasing, right? So if you see a function like this, that's decreasing. But it should increase or decrease all the way to call a function monotonic, strictly monotonic on an interval. Okay, let's keep going, and I think the next section was talking about the first derivative test. This is again one of the most important results here that we use towards like 4.6. Let's say like you have a critical number to start with, and f is continuous and f is differentiable on the interval. It doesn't need to be differentiable at point C, because that's a good candidate of a critical point anyway. So if f prime changes from negative to positive, okay, here is a representative example here, then f should have a relative minimum at the critical point. Okay, so this is sort of like how you determine if a critical point is giving you a relative minimum or maximum. Okay, so this is again for finding relative extrema by looking at the first derivative of the function. So decreasing and increasing behavior, and C is the point where you hit the bottom, as you see in the valley. So that means it's a relative minimum. Or like in the second case, f prime changes from positive to negative. That means it's increasing all the way, as you see, but all of a sudden it starts decreasing. So C should be a relative maximum. And in the third case, it just says that if f prime doesn't really change its sign across critical points, then probably you don't have a relative maximum or minimum. Okay, like in this example, it's increasing all the way. You hit the critical point and it keeps increasing, so this doesn't really tell us anything about relative extrema. In fact, they don't exist, and in this case as well, in a decreasing sense. Okay, and this is called the first derivative test, and make sure that you are able to answer the questions being asked in the homework assignment to pinpoint relative extrema by using the first derivative test. And we're going to have a second derivative test, but just hold on a second. Let's keep going, and the next concept that we dealt with is concavity. So concavity is like how curvy a curve is, essentially, and this kind of like behavior is determined by the second derivative of the function. Okay, remember, like so far we only worked on the first derivative based on finding its critical points or determining its sign to find relative extrema. So now for concavity, we'll be working on the second derivative of the function. So we say like the graph of f is concave upward whenever f prime is increasing, whenever the slope is increasing, slope of the tangent lines, and also it's concave downward whenever f prime is decreasing on the interval. So now how do we determine concavity? By looking at the function expression. Well, you first find f double prime. Okay. If f double prime is positive, then you have concave upward behavior on an interval. And if f double prime is negative, then f is concave downward on the corresponding interval. So again, what we're going to do to determine concavity is to check f double prime, okay? And we look at the sign of f double prime on the subintervals, okay? All right, the next thing that we talked about was points of inflection, and that again comes out of the second derivative of the function. So inflection point is the point where the concavity changes, essentially. So if you see like concave upward turning into concave downward, like in this case, right? So that point is a good inflection point. Or concave downward behavior turns into a concave upward behavior. Again, that's the same kind of behavior. And same as here, even though you have a vertical tangent line, concave upward behavior turn into concave downward, so you have a good inflection point right here. All right, so we covered the first derivative test earlier, and we were using f prime to determine relative extrema. There's an alternate way of pinpointing relative extrema. It's called a second derivative test. So we still use the tools of critical points, obviously, on this, because here our assumption is that f prime of c is equal to 0, and we want the second derivative to exist on the open interval containing c to get to that conclusion. In fact, if f prime at c is equal to 0, that is in fact a critical point of the first kind. So once you pinpoint the critical points, especially the first kind in the analysis of f prime, then you can test those points if they spit out a relative minimum or maximum values. Okay, so all we're going to do here is to check f double prime, the sign of f double prime, and if f double prime is positive, then you have a relative minimum for sure at c, and if f double prime is less than 0, f has a relative maximum at c. So what happens is that if f double prime turns out to be 0, then this test is inconclusive. Okay, so you can't really say anything about c, whether or not it's relative extremum value. Okay, so then you have to go back to the first derivative test. All right, so this is a complementary of the first derivative test. In fact, I would just start with the first derivative test when the question asks you to find a relative extrema, and then I can also use this information to sort of like verify exactly what first derivative test spits out. And then sometimes these two tests are used like simultaneously. Because as you see, like the second derivative test may fail, especially when f double prime is 0, as you see. It's inconclusive. I would totally recommend you to use both of these tests whenever it's applicable. And the next section, that was like 4.5, I believe, and we talked about limits at infinity and horizontal asymptotes. And here, there is the epsilon definition of the limit. I wouldn't really worry about this definition. But just keep it in your notes, not in your formula card, but in your notes, because we don't really use this definition. But for your own understanding of the concept, well, yeah, feel free to read it through the text. And what the important things are here is the definition of horizontal asymptote and those limits of known functions. And here, if the question is asking you, like, find the asymptotes of a given function, then and obviously you don't have to find the vertical asymptotes because we covered that earlier in calculus. So for horizontal asymptotes, all you're going to do is to check two limits. One is the limit at x equals negative infinity, and the other one is at infinity. So if those limits turn out to be finite numbers, then you can conclude that y equals L, which is the limit value coming out of this calculation, would be a horizontal asymptote. Okay, and these are the known limits. As you see, if you have a constant, let's say c, and a positive number r, positive rational number r, c divided by x to the r takes you to 0 as x goes to infinity. And as x approaches negative infinity, c over x to the r takes you to also 0. Okay, so that means like the bottom gets extremely large because you're taking the positive power of x. So essentially, the top is constant, the bottom is growing without a bound. So you are going to end up at 0. So in those cases, y equals 0 would be a horizontal asymptote. Okay. And the second limit, the second property here is that you have exponential function e to the x and e to the negative x, and those functions have horizontal asymptotes. In fact, e to the x has a horizontal asymptote as x approaches negative infinity, and that horizontal asymptote is equal to y equals 0. In fact, y equals 0 is the x-axis. So x-axis in all four cases here, including these limits, would be horizontal asymptotes. Okay, so check this out. And the next thing is the guidelines to sort of like finding the limits of rational functions at plus or minus infinity. And we again use this kind of like guidelines all the time. So let's say like you have a rational function, let's say p of x and q of x divided. Let's say like the first one says that if the degree of the numerator, okay, so these guys are polynomials, so you check the highest order, highest power term, and that's the degree of the polynomial. So if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. So you're going to write here that plus or minus infinity is going to be 0 for the first case. Okay? And in the second case, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is going to be the ratio of the leading coefficients of the numerator and denominator. Right? So let's say like you have 2x squared plus 1 divided by 3x squared plus 1. As x approaches plus infinity, let's say, then the leading terms are 2 and 3, so the ratio is going to be 2 over 3. So that's the limit value. In fact, y equals 2 over 3 in this case is going to be the horizontal asymptote. Okay? If the degree of the numerator is greater than the degree of the denominator, well, the limit doesn't exist. It could be either plus or minus infinity. Okay? So in this case, y equals 0 is a horizontal asymptote, and then in this case, y equals whatever that ratio is, okay, that is the horizontal asymptote, and then in the third case, you don't have a horizontal asymptote at all. Okay. You can skip this part as well, so like the definition of infinite limits at infinity. So this part is important because it talks about how, this is 4.6 by the way, in the homework assignment. This is homework 20, and this is a kind of homework that you should really pay attention because you wrap up all of the things that we learned so far and use them in 4.6. For example, the first thing that you're going to check once the function is provided to you is the domain and the range of the function. This is done in pre-calculus, but make sure that you know the domains and ranges of known functions, and that's done in pre-calculus, and you make sure how to find a domain and range, in fact, and once your function is a composition of the known functions. Okay, this is again done in pre-calculus, and the second part is somehow like done in pre-calculus partially, like intercepts and intercepts and symmetry, and these are done in pre-calculus. When I say intercepts, I mean like x and y intercepts. And when I say symmetry, it's x-axis, y-axis, and the origin type symmetries. And asymptotes, vertical part was done in before, and the horizontal asymptote part was done in this section that I just mentioned. And there's also something called slant asymptote, and this is also mentioned in 4.5 lecture notes. Make sure you go through my video on slant asymptotes, so that's the third kind of an asymptote. Okay, And in number 3, all you're going to do is to find f prime and f double prime to determine critical points and inflection points. And those points are going to help you to pinpoint a relative extrema of the function. Okay, so you will have the domain and range, symmetries, asymptotes, intercepts, and increasing, decreasing behavior, and concavity, and inflection points. So once you sort of like bring all of this information together, you can in fact tentatively graph the function based on the data coming from these guidelines. Okay. And then finally, we had the tangent line approximation. So if you are given a curve which is differentiable at the point C, then you can write down the tangent line to the curve at the point C as y equals f of C plus f prime of C times x minus C. So this is in fact the point slope form of the tangent line. You just solve it for y. Okay, so this equation here is called the tangent line approximation, or the linear approximation of f at C. So if f is a too complicated function, let's say like sine x to the power of 1 million divided by ln x plus x to the power of zillion. So if the expression of that is really complicated, all you can do is to approximate the function at the point C by using this tangent line approximation to estimate the values of the function, especially when you don't have any calculators with you. Okay, so how do you know the value of the function at a fixed point C, for example? So to estimate that, you use this approximation. Okay, and then finally we talked about the differential concept. Here. So let me just clean. All right. Finally, we talked about the definition of differentials. If you have a differentiable function on an open interval containing x, the differential of x, denoted by dx, is any non-zero real number, and differential of y is denoted by dy. So it's essentially infinitesimal change in x and infinitesimal change in y. That's exactly what you call it. Versus rise and run concepts, right? To find a slope, you have the rise and run, right? But if you think about the rise and run in a very small scale, so that those turn out to be dy and dx, infinitesimal rise and infinitesimal run. Okay, that's why we compare them here. Okay, this is sort of like your rise, and then this is infinitesimally small rise, and this is run, and generally delta x and dx are taken to be equal to each other. Okay. And the actual run of the function is approximated by f prime of x dx. In other words, the actual run is approximated by dy. Okay, but it's infinitesimally small run in response to an infinitesimally small. Infinitesimally small rise in comparison to infinitesimally small run. Okay. And finally, these are the differentials of known functions, and remember the properties that we had before from differentiation. So essentially, if you know the functions, and all you can do here is that using the constant multiple rule or sum or difference rule, product and quotient rules to determine the differentials of products, quotients, and sums or differences and constant multiples. Okay, so I hope this sort of like review lecture notes is helpful for you to have like a good digest of differentiating what is important versus like what is not. So whatever goes into this review PowerPoint notes would be extremely important, and make sure you understand those concepts and know how to apply the guidelines here. All right, that's the end of the video. Thanks for watching. I'll see you in another video. Bye.